All right, hello everybody. My name is Ari. My presentation is called Climber for Scale, Engineering Geology from a Rock Climber's Perspective. So I'm a geological engineer and I'm also a climber. Been asked to give a presentation about both of these topics, and the way I'm going to do it is show you guys some pictures from some climbing adventures I've been on and talk about the geology in the background. The goal here is just to kind of motivate and inspire all of you to just look around the landscapes that you're in and try and figure out what's going on. It's fun and rewarding, and I think it also helps us all as geo-professionals as we try and understand the subsurface. So, like standard presentation, here's the outline. Spend a little bit of time talking about how rock climbing works for those of you who aren't familiar with it. We'll talk about bedrock fracture patterns, how regional tectonics and local structural geology shapes the landscape. And then I'll spend a little time looking at some glaciers, what they look like in real life now, and what the signs they leave after they've gone. So let's get into how rock climbing works. The main thing I want to sort of convey is that there's a system here. It's pretty safe. I mean, accidents happen, but if you ask most climbers, they'll tell you they don't think they're taking their lives into their hands every time they go out. And this is how it works. The first person up is called the leader. They tie into a rope, and as they climb, they run it through pieces of protection that are either fixed like a bolt or pieces of cams that they can put in and they can later be removed. And there's somebody at the bottom called a belayer. They feed the rope out, and they've got it running through a device that they can lock off it if and when the climber falls. So if you look closely, this is a picture of me right in the middle of a fall. I was just up there grabbing onto a hold that came off a little higher, and now I'm whistling past my last piece of protection. The rope's about to come tight. And luckily that rock didn't hit anybody. We weren't wearing helmets, we should have. Everybody was okay, so it works. Then when the leader gets up to either the top, or if the cliff is a big one, just to a natural stopping point, they'll anchor in and bring the belayer up, and that's called the follower, or someone who's top roping. That person will come up, clean out any removable gear, and when they get up to the first leader, a lot of times they'll become the new leader and make it to and continue on to the top. And the team will kind of inchworm, leapfrog their way up until they make it to the top, or I guess you're gonna have to bail and go down, but hopefully you're making it to the top. So that's how that works. Now we'll get into a little bit of the geology part. First, I just want to talk about discontinuities or cracks. Perhaps like the most kind of obvious bit of geology in rock climbing is the actual cliff face. And these cliff faces, are often formed by the dominant joint sets. Usually you have a handful of patterns that all follow similar orientations, and they form the cliff face. And you can recognize this. So I'm going to do some little shading here to show what I mean. So you look down the climber, he's climbing this. I'm going to highlight the face. It looks pink here, and you can see those same discontinuity orientations reflected in the faces as cracks on the walls on either side of him. Similarly, the climber is climbing cracks, and I've got those shown as blue lines, and you can see those same crack orientations are forming the face on those walls on either side of them. You can zoom out here. This is just earlier in the day walking into that cliff face. You can see kind of this splintery look, the peaks, the recessed area in the middle of between them. It's all sort of formed by these two dominant joint sets. So it's just right out there to look at, and it's just sort of fun to recognize. This is another photo. This is down in southern Utah. Once again, you can see like these subvertical fracture patterns sort of, intersecting and forming the towers. The other thing you can see here is this is, you can see this is sedimentary bedrock, and you can see the horizontal bedding planes kind of in the towers, but you can really see them in the slopes below them with these cliff and slope forming units below. So this is Castle Valley, Utah. It's a huge climbing destination. It's just about 20 miles up the Colorado River from the town of Moab. It's hard to see. I don't know if any of you guys have seen it, but there are 4 climbers in this photo, just to point them out for scale. I'm actually the guy who's second from the top there, just bridging the gap. And I'm going to go into I'm going to stay in Castle Valley here and look at a couple photos. First, I just want to point out, like, this is just iconic, point out the regional geologist, is just like iconic, stereotypical Colorado Plateau scenery. So this area covers southern Utah, Arizona, Colorado, New Mexico. And it's all been uplifted over the last 20 million years, about 5,000 to 8,000 vertical feet. And as it's come up, all the sedimentary rock's been uplifted, it's exposed it to erosion, and these towers are just these erosional remnants that are sticking up. You can see it's really dissected topography. A lot of the erosion is happening these days with flash floods and dry washes. Remove massive amounts of material in short periods of time. Often on the left side of the photo, you can see some of these dry washes. Next photo here is also in Castle Valley. This time we're over on the convent, which is in the back there, looking back towards the priest and the nuns, which are these towers in the foreground. So here we are nearing the top of the convent. You can see the priests and the nuns are marked out there. They're kind of hidden in front of the rectory. Castleton Tower is just another great climbing spot, just because it's a big pointy tower up on a hill. And then there's Sister Superior in between. But once again, it's looking the other way. You see this really, really stereotypical Colorado Plateau topography with these really dissected drainages. But, I'm going to use this photo here to point out some local structural geology. And if you look in the back here, I'll highlight it even more green. I'll kind of flicker it back and forth. But you can see this valley back here, the texture looks a little different. It's just sort of a different appearing thing. And there's some geologic structures here that are responsible for that. This is Castle Valley proper back here, and this is actually a failed salt cord anticline. And we'll go in a little bit into that with this next slide here. This is just the geology cross-section from the published quad map of the area. Luckily, the priests and the nuns are on it, so you can use it for this presentation. You can see the salt cord anticline off to the left there in Castle Valley. So back in the Pennsylvania, which was before the uplift of the Colorado Plateau, this area had a closed ocean environment. So this ocean dried up repeatedly and left these really thick salt deposits as it evaporated. Well, this got eventually buried by the sedimentary rock that you can see in some of those other photos. But the salt, being less dense than the overlying bedrock, kind of rose up through it buoyantly and kind of humped it up into an anticlinal fold in this area, Castle Valley. As it warped outwards, it cracked, and it was a topographic high spot, especially after Colorado Plateau uplift. That left it more susceptible to erosion, so this topographic high, then it was preferentially eroded into a topographic low, and became, I'll go back a second, and then became Castle Valley. So what I'm going to do here is kind of manipulate this photo and drape it on that last one just to kind of help you see it. So here it is, flipped around, squished, and then draped. Yeah, I got my Gen X computer skills here. So you can see right there where I've got so I lined it up on the priests and the nuns butte because that was something we saw earlier. And you can see where the bottom's dropped out of that valley. You can see the porcupine rim, the edge of that anticlinal fold that's left standing. So, just have a look at these things. They come out at you. It's really interesting. And then this is the last bit I've got to show you here. It's just going from the desert up into the mountains. And this is over in the Coast Range of British Columbia. This is the Tiedemann Glacier. And just look at these glaciers here. So this area is in the Coast Range. It's got enough latitude, it's got enough elevation, especially on the high peaks, and it's got enough precipitation where we've all learned this before, right? Glaciers are just an area. They get way more snow that can melt during the warm season. And the snow has got only one place to go, and that's downhill. It compresses into ice and flows, and glaciers are just rivers of ice. The analogy sort of extends instead of the rapids. They're ice falls instead of waterfalls. There are seracs, and they're pretty amazing to see in real life. These things carve out valleys. They flow downhill and coalesce, and then they carve out these broad valleys. Ice carves these flat-bottomed U-shaped valleys, whereas a river would carve out more of a V-shaped valley. And we'll take a look at that here. This is just another photo over on a route we did on Tehipite Dome. This is in Kings Canyon National Park, looking down at the middle fork of the Kings River. And if you look down in the background, you see this nice flat, broad valley, and all of a sudden it changes into a V-notched valley. And going back to that last photo, and what we've learned is, these glaciers carve out these flat bottom valleys, and when they stop, it'll turn into a river and carve a V-notched one. And sure enough, I'll pull up the quad map here, or the published glacial extent map for this area. So you can see Tehipite Dome, that's what we're on there, about halfway up this 3,000-foot cliff looking down. And just to the southwest, you can see the Tehipite Valley Glacier going down the middle fork of the Kings River. This is the maximum extent of the alpine glaciation during the last ice age from the High Sierra down to the west. And it just sort of ended there because it got too warm and turned into a river. And I'll do the same little trick here, I'll flip it around and kind of superimpose it, and just to show you that we're looking at the map right here and what other people have interpreted. So that's basically all I got. All the things I've shown you today are pretty basic Geology 101 kind of stuff, and that's kind of the point. This stuff isn't super hard to do. It's just going out there and doing it, kind of developing an eye for it. The other thing is, it's never been easier to look up the geology of an area, and just see what other people have done and interpreted, and then you can sort of internalize that. And not only does it sort of make it more interesting to go through life looking at these landscapes around us, but I think it helps us all in our jobs when we're trying to figure out what's going on at a certain job site. So I included this picture of my buddy Brad here. It's just a reminder to sometimes just kick back, take it all in. Thank you.